Okay, so we are kind of, seems like a never-ending story. We keep digging deeper into classes, but really, since we're supposed to be doing things in an object-oriented way, it tends to be like actually the main point. In fact, college courses are starting to change in the introductory levels where they're just kind of starting out with classes right off the bat, which I think is a little challenging. Some of you might remember we didn't really start looking at classes until the end of our Comp 130 course. But really, a modern program is all about classes. So it's kind of hard to escape that theme, and we'll just try to keep filling around the edges on that stuff. To remember, I think everybody's doing great. Totally fine to email me for recommendations, things in Outlook, but otherwise, we'll try to keep things in Canvas. Homework one was due Wednesday because of the power outage. So this is a little bit out of date. So this will be last call will still be Sunday, right? So you want to get it in Sunday for 50% off, but you got a free day there the other day. And I think most everybody's doing pretty good. I'll try to get those things graded right away tomorrow morning. Usually that's when I jump on top of grading right away. And so quiz one was also Wednesday. So everybody should have had 3 tries on that. So thanks for pulling through. Actually, everybody did pretty good despite the chaos of Tuesday. So that was our lab 5. You have until Friday night. And then we're going to do another out of class implementation multi-file for lab 6. Now I have come up with a way that you can do it all in one file in the Program IZ online compiler. So it's okay for you to do it that way, because I know it's kind of messy sometimes getting our account set up. But you'll be better prepared for the world if you can do these in separate files at some point in a pro version of Program IZ or Visual Studio Pro or something like that. So anyway, in 2 weeks, we will have tic-tac-toe. Some of you started thinking about that already. I'll slowly start nudging you in that direction, but feel free to peek at that and start thinking about that soon, because we're going to want to implement a tic-tac-toe.h and a tic-tac-toe.cpp. And so the things we talk about today are exactly what you need to know in order to understand that homework. So pretty much after today, I think you'll be ready to jump on that tic-tac-toe if you want to actually do that. Okay. Now, you hear me talk about this a lot, but every time I see one of these cars, man, it just blows me away. It is a walking, talking, inside out video game. I mean, trust me, it's like it's got graphics hardware, it's got AI hardware, it's got, essentially what's a GPU, it's C++, specialized hardware, lots of sensors. It's serious math. It just blows me away to see these things driving around. It's a little scary too, but holy cow. And it's always fascinating. If you got some passion around a company, go look at their job listings. Don't worry if you can't do it now, but set your sights. Do not undersell yourself. The way I got into my career was I just thought video games and special effects were cool. I knew nothing about them. And I just kept hammering away until I got where I felt like I wanted to be. It took some time. I kept trying to take the classes I wanted. I didn't always do great, but it's good to know what these companies are looking for. And, it's always a little intimidating when you see PhD or, you need to be a data scientist, but there's a lot of information in these job descriptions. So I find out a lot of things about companies that they don't even realize they're revealing by looking at who they're hiring. So I would say, every once in a while, take your favorite company, go to their careers page, and just sort of quick scan and see, where are they hiring? What are they hiring? What kind of degrees do they want? Sometimes you might be surprised. They might have an internship they're throwing out there. So this is my idea of the closest device out there that comes to what we're doing with C++. Lots and lots of intense coding and a focus on performance. So, and that is kind of unique to C++. There are other languages, of course, that you could deal with higher order kinds of things. Many game engines have scripting engines, and probably at some point, a car like that is going to have a scripting language. but at its core, it's going to have a high performance piece of software written in a language very much like C++, and probably with even more optimization at the low level in assembly code. So for those of you who have taken Comp 160 or are thinking about it, people still do dig into the assembly and move little bits and pieces of code around to make the inner loops go really, really, really fast, right? So sometimes you might actually even want to optimize what the compiler is doing to make it go faster. When I worked at Havoc, it was a real-time physics company based in Ireland. We had a developer who loved compiling for the PlayStation 2, and then he would get in and look at the assembly language and just make it go even faster by tweaking that low-level function that was just being called a bazillion times. So, this is cool stuff. It's high-performance stuff. Doesn't mean you have to do that kind of stuff if you're using C++, but it gives you a sense of why we have languages like this for doing that kind of computation. Okay, so real quick review. I know some of this you guys got pretty quick. Remember that our constructor initializer list is just this other way of initializing all the data members of our class. So the data members in this case are our capital letters, and they're all up here, and you can kind of see the order that they're in, A, B, C, D. Normally, we don't really care about that order. Some of you encountered an error or a warning where it was saying, hey, you might have done these out of order. Maybe you did this one before you did this one, and originally they were in this order. Normally, that's not going to really hurt us, and so we'll show you a trick to get around that. But if you want to fix it, just kind of go back and redo these things in the order that you have your data members in your class, and that little error thing will go away, okay? So keep that in mind, okay? And notice that we really don't have a default constructor that we have to add here, right? We sort of have everything handled by virtue of our default values. So we could call this constructor with no arguments at all, okay? So all sorts of games we can play with that. Now, if you want to get rid of these compiler warnings, if you're using Replit, find your makefile, and I'll show you where that is, and just remove that flag W error. So if you see that thing, that's really a setting that many developers use when they're getting ready to release software out into the world, and they want to be extra sure that even little maybe warnings actually stop your compile so they don't accidentally sneak out into the world and create larger problems. So you can kind of remove that W error in your makefile. And again, I'll show you where that is for Replit here in just a second. Or just reorder these things to get rid of that warning, okay? So either of these are perfectly fine, and then you should be good to go. Now, last time we talked about out-of-class implementations, we said, hey, we're going to set up our prototype of the whole class here. There'll be no curly braces in here whatsoever, not as far as the guts of any of these things are concerned. But we're going to do it over here, and we have to prefix the name of our method or the name of our constructor with the name of the class, and we call that our scope resolution operator. And it's kind of weird because the return type goes on the far left, okay? And notice also that my default for my second argument over here is not in my CPP file over here. It's over here in my prototype. We'll point that out a couple times here today, but that causes all sorts of confusion in our homework because it's like, oh, okay, I copied my prototype over here and I forgot and I left the equals X in there. And now the compiler is saying something weird you don't understand. And all it's really trying to tell you is get that thing out of there. I already know what to do over here and we're good to go. Okay. So keep that one in mind when you start digging on your homework. Now, a brief word about makefiles. We really don't have them right now in our Program IZ Pro. They are an important thing out there in the world. We don't really spend a lot of time on them in this class. We probably should. But in Replit, if you kind of open up your hidden files, you can kind of see this thing over here called a makefile. So a makefile is this set of instructions, almost like its own other language that tells the compiler how to snarf up all of these CPP files. It basically says, hey, look around for a .cpp file and glue them all together in the following way. And some of those those flags, that dash W error is like one of the kinds of instructions we give the compiler. This is like, hey, this is the master chef or the sous chef in our restaurant who's putting together all of the things. And so these are the high level instructions on how to build this final program. So something like a Photoshop or Chrome, I assure you, Chrome has a make file. It's probably huge, right? Because it's probably got so many separate files that actually build that thing up together. So again, we won't do too much with make files in here, but it's important to know what they are. And this is just one kind of opportunity to dig in there and see what it looks like. So if we looked at our make file on Replit, we'd see, okay, if I want to make everything into an executable called main, that's going to be built up from this target called all, right? Or sorry, all is going to be built up from this target called main. And main is going to be built up by filling in all of these definitions. And sources is here and headers here. So you can kind of see it's just another language for filling in variables and expanding things, okay? And so we won't go through all of this, but this is a pretty long-standing way of actually managing large-scale compilations where we're pulling together many files, okay? Not something we specialize in this class. If you've ever wondered, like, how does the run button in Replit or Program.iz know how to do what it's doing? A lot of times, somewhere in the background, there's a makefile helping it know the rules, okay? Once upon a time, that was all there was. There were no Program.izs or anything, and we all had to edit our own makefiles, and won't bore you with that story. So today, we're going to look at a lot more examples of classes and talk about data member access, private and public. So very quickly here, especially as we think about our risk game, it's like you making a class, I'm making a class. They all have private data members, but what if we got to reach into each other's classes and print something from the other class? How do we actually have that kind of access? So we'll look at doing that. We'll look at more of our, managing our .h and .cpp files, and we'll build a simple car that is comprised of several parts. So we'll see that class composition is a way of making a car whose data members, its actual data members, are other classes. And that is very different than actually having a car whose data members point to instances of other classes. These are two different strategies. One involves creating an instance of a wheel or an engine inside of my car, and another one says, well, we're just going to point to this other piece of memory that represents the engine, okay? Two perfectly valid ways to actually build data structures, and we'll explore both of them kind of over the course of this whole class. Now, today, the other subject, really easy one, is called friends. Two classes can declare each other to be friends. And that is one way we open up access just between those two classes. Maybe the car needs to reach into the engine and find out how much horsepower the engine has, right? And it doesn't want to use a getter, for example. It just wants to directly access a data member of the engine. So we would need to do something if that engine's data members were private so that the car could kind of reach inside of that class. And friends is one of those ways we're going to actually do that. Okay, so those are some of our things we're going to cover today, but mostly we're just going to see more examples of the .h and the .cpp separation. Okay, so we'll call those prototypes and CPP files. And we'll show you here in just a second that really what ultimately happens is all of those things end up back in the same file. The .h ends up on top usually. All the guts of the .h end up stacked up here, and all the guts of the .cpp get glued in just below it. And you might be thinking, well, then why do I have to go to all this trouble to separate this stuff out? So we're going to try to demystify that for you over the next couple lectures, okay? So remember, we're dealing with blueprints, pretty much the class name, the data members, the constructors, and the methods, and their default arguments. So that's the key thing to remember. And then we have no guts, no curly braces, okay? So these are the rules for the inputs and the outputs along with their defaults, and we'll just consider that to be everything but the implementation, okay? And that's our .h file. Or we could just put it all in the same file and call it a prototype if we want. And then later, usually in the CPP file, we have the out of class, or sometimes I say OOC for out of class implementation of like our constructor, etc. So we'll look at that again today and see how we use that. So some things you might say is if you follow the prototype when you use my class, I promise you, you will never have to rewrite your code. So let's think about this. You decide you're going to make a game with the Unreal Game Engine, and you're going to use version 3, and you write this amazing game, and you're making millions of dollars. Your life is great. And the Unreal Game Engine decides it's going to do an update to make everything go faster. So your game can go faster. You can have more characters running around. But they decide that they're going to change the names of all of their methods, right? They're going to decide to capitalize them or something. Now you have to go change all of your code, okay? And that's kind of annoying, right? So not only do you have to change your code, you have to recompile it and you have to relink it and all that stuff. So very often what commercial developers do is they promise they will not change the prototype, but they might change the implementation. Like, how does my constructor do what it does on the inside without changing how you actually create an instance of a car? And that's a really good thing. That is a really good thing. Many of us have had our video games fail or our Apple apps fail on our phone. We think, why do I have to download this again? Well, that's because typically they change their prototype. And maybe they kind of had to. They got up against a wall. But the name of the game in commercial software is design an excellent prototype and hold on to that as long as you can. Make the guts of it better and better, but don't change the prototype because your developers are going to have to go out and change all their code and they're going to get really frustrated. Okay. So that is really just another possible advantage of all of these things, right? So this is our contract and it serves a lot of purposes. Now, as we work with these files, we're going to see more and more of this include thing. And I got to tell you, I didn't really understand it fully, or if I did, I forgot. But it seemed like for years I was using it and not really understanding what was going on. I thought that a .h file was like, this file that the compiler went looking for. I thought the compiler, understood that file was like some CPP file, right? So we've been loading libraries and kind of thinking, well, I don't know what that does, but I need it, right? Maybe we didn't even understand what it was doing. Here we're going to see exactly what's going on. So it turns out that include is a giant copy paste monster. It's going to go out and grab that file and copy and paste its contents exactly right here. So if this was one line, it could expand to be 1,000,000 lines, depending on how big that file is. And it doesn't matter what the extension is on that file. It could be .bananas, right? So we call it a .h as a tradition in computer C++ development because that helps everybody remember, oh yeah, those are the prototypes for my class, okay, or some kind of prototypes. So we'll see how that directive is not really part of the C++ language at all. We call it a preprocessor. It's like a giant robot that sort of works before the compiler starts crunching all of our C++ code. So if you see a pound something, that's a hint that that's a directive for the preprocessor, and it happens before the compilation starts. Okay, so that might help you sort of demystify things. So we will be including things into our CPP files that are typically .h files, but we will never be including a CPP file into another CPP file. Generally, that is just a door for problems. So let's take a look at kind of a brief animation of how that works. So here's our .h file over here. This is our blueprint for some foo class. It's got a constructor and some methods, no curly braces, right? And over here, I have my foo.cpp. And the compiler needs to know what foo is before we can talk about foo. So just doing this without this would be a problem. But when I say pound include, it is literally a giant copy paste machine. So what happens is the preprocessor comes along, throws away the pound include, and overwrites it with an exact copy of our .h file, okay? So you could write this equivalent code by literally skipping the .h file and just putting the prototype above your out-of-class implementations. So as a lab experiment for today, if you don't want to use Program.IZ Pro or Replit, you can just use the online compiler and do it this way. Just keep in mind that this is conceptually our .h, and this is the rest of our .cpp right here, okay? But that's what our include file does for us. Now you might say, well, why shouldn't I just put everything in there? Well, your friend, uh, you know, uh, Brianna over here is like needing this as well, okay? Because she's going to do some development based on the foo class. So you got two developers needing to load in the same .h file, and we do not want it changing, right? And if it does change and somebody changes this to a lowercase b, guess what? The include directive will pull that in at the last possible minute so that both or all developers are actually going to get the same copy. That's why we're extracting that out of our CPP file, because that has got to be shared by our entire team. And so when we get to really gluing together our RISC parts, we are going to have a bunch of .h files, and a lot of us are going to be grabbing .h files from other teams and putting them in our code. And so hopefully those .h files don't change too much, because they will break all of our code. And so we'll experience that when we get to that point. But that's what our pound include is doing. And that's kind of why we do it, so we can work with these larger teams. But the compiler really only ever sees this, okay? So this is what we call a compilation unit. So the compiler crunches that all together. It forms a little .o file. And then eventually we glue together all those .o files together into our final program, right? So the pound include thing isn't really, or the .h file doesn't really get compiled. It gets pulled into our CPP file, and that gets compiled, okay? So that is kind of the big thing that I really didn't know in the beginning. So let's take a look at how this might look. So here is our main.cpp file, right? And I want to create an instance of the foo class. So main has to have some description of what foo is. So it's going to include the foo.h file over here, right? But I also need to include foo over here inside of my foo.cpp so that I can build that particular chunk of code, and it can be then glued together with this other one. So the directives, the include directives, are going to pull these pieces of code in for me. The compiler is really only going to study the resulting .cpp files, and it's going to compile them and then link them into a final file, what we call, typically we refer to as main, right? It's an executable zeros and ones that we run, and then all of our good hard work produces cool things like a driverless car driving around San Francisco, okay? But that's the name of the game that we're playing. We will use these .h files knowing that the compiler or the pre-compiler is going to come along and glue them all together, build them, and get our final executable out of that at the end of the day. Okay. And so for things like Risk or chess or anything, even tic-tac-toe, we may have 3 or 4 or 5 or 100 different little tiny compiler unit files. We call them .os sometimes. And once those get built, then they can all be glued together and form our final thing, okay? Questions on that before we kind of forge ahead? Okay, all right. So let's talk about a couple of specific examples. Let's look at an ancestor. This is really just a person. I often think I got a little bit interested in ancestry and that whole thing because there's so much data involved there. But I thought, well, what would it look like to create a class? So this is our .h file. Okay, notice there are no curly braces anywhere, okay? So we can tell right away this is not an implementation, it's just a prototype. Okay. But we have string, int, year. So these are pieces of data that get allocated when the class is instanced. So our data members need to be created when we get an instance of the class. This is the factory, right? But when we create a version of this, right, we get all of this kind of good stuff created inside of it, okay? And there's our 4 methods, but no curly braces. So ancestry.h has that. And then we do our out of class implementation, of course, over here. And we have to include our ancestor.h in order to do that. We still don't have main, right? There's no main here yet, but we have 2 really important parts. Now in Java, for those of you who may or will take Java, Java doesn't have this kind of separation. You create an individual file, and Java itself, which is not a compiled language, will actually do this kind of checking between prototype and non-prototype automatically, but it's a completely separate process. So this is very specific to our CPP or C++ that we're working with. Okay, so let's see if we can actually do a few of these. So using one of these, you can either use Pro or you can use this Replit, or you can just sort of follow along. It's not absolutely critical that you do this if you don't have your Pro login, but it will be easier if you have your Pro login or if you have your Replit login going. But our declarations are done, and we will do all of our work in ancestor.cpp. And we want to do our constructor, okay? And our defaults are in the prototype. So if you copy the constructor's prototype from the .h, don't bring over or remember to erase those defaults, okay? And also the other thing we mentioned is we don't do the using namespace. So when you do your print me, you're going to be really tempted to go, oh, I need to set my using namespace, but we want to use std : before the cout and before the endl and all that stuff, okay? So I'll show you the solutions for this piece at a time. So let's look at our prototype file again, right? So there's our .h file right there, okay? And notice we had to include string up here. It's really annoying, but it's like, oh, I'm in the .h file, but even that thing needs to include a string because I'm referring to a string type. And notice I have std : here. I'm not allowed to use the using up here, okay? So that's key. And annoyingly, we got to do it here, right? For all of our data types that are kind of part of the std class or std namespace, okay? So that's our .h, right? Okay. And also there's our defaults. We can see one default there. We will not carry that over into our CPP file, okay? And here's main. So now main needs to include .h because if we try to create an instance of our class, like a grandfather, right? Ancestor space GF, pass along some arguments, then we now have an instance, but we have to teach the compiler what that means, right? The compiler won't really understand how to do type checking on that. So once we do that, that's really cool. And we can even call the methods that are inside of there, right? So that works. So some of you were asking last time, can I just use a forward class reference? And the answer is no. Like you can say class ancestor, but that is not going to let you do something like this, right? The compiler is going to scream at you. So really the forward references, if you don't know what that is, don't worry about it. But forward references don't really get us where we need to go. We got to kind of have this .h thing going on, okay? So that's our main file. Let's take a look at our out of class constructor. So this is all in the ancestor.cpp file. Kind of all of these slides I'm going to go through are all just floating out there. See, it's not inside of the class. There's no class ancestor here. It's just ancestor : etc. Right? No defaults over there. And then we got to have our, let's say, our constructor initializer list. and our empty curly braces, because there's really nothing else to do here at the moment, okay? And you can say title equals T, okay? And what's confusing is that without going and looking at the .h file, you might forget what the name of your data members are, right? So very often you're flipping back and forth and going, okay, wait, what are my data members? Got to go all the way back, right? Oh yeah, okay, it's title, year born, died, etc. The colors are off there, but kind of get my meaning there. Okay, so that's our constructor. And don't forget this, that's going to really mess you up on some homework, so I'll remind you. And then, of course, you can kind of go on and do all your other methods. But this is the flow. I just wanted to reinforce that because we just saw that for the first time really in our lab last time. Okay. Any questions on that before we take it up a notch? Okay, very good. Good one to come back and practice on. So let's talk about this idea of class composition. This was another big aha moment for me. Like this really was like, really? What? Is that what it's doing? Like, and it just, didn't know. So let's talk about a car. So I have a car and I want it to be a red car, right? And I want it to be going at a certain speed. Okay. Now our car has lots of parts. And so I would love to like divide and conquer with my giant team of developers and build a car. So I want you to build the engine and you build the wheels and you build the carburetor or whatever else, right? In fact, we could just get more modern and say, hey, let's create a virtual car, electric car in software. How would we actually do that, right? So we got all these other things and they have their own attributes and their own constructors as well. So how do we bring all these things together, okay? And there's more than one way to do it. So we're going to look at the two primary or two extreme approaches. One of them is to just think of E for the engine as a data member inside the car. Car always has one engine. So I have a data type called engine, and the letter E is the variable or the name of the data member that is the engine. Now, of course, that engine has data members inside of it, right? So I have a car and then a .e, and there could be other stuff inside of the E there, right? Same for the wheel, but I only have one wheel there, right? So there's a W. Probably, if this is a unicycle car, apparently, I should have been like W1 and then a W2 and W3, but those are individual instances of the class. And there's my radio. But we could have also taken this approach. We could have said, I'm going to want to, have a pointer to the engine, which is a dynamically allocated thing floating on the heap. If you remember the heap, and we will review that a little bit. But so engine star is saying, I'm eventually going to hook up a reference or a pointer, not a reference, but a pointer to an instance of the engine. But by default, my data member is just a 64-bit space holding an address in memory, or eventually it will, okay? And then we will go create this probably in our constructor for the car. So the constructor of the car has some work to do over here where we have to write the code to kind of build out all the parts. Where over here, it's like, hey, there's always going to be one engine, one wheel, and one radio, okay? So these are kind of the two extremes, and we could blend them a little bit, but the tricky thing on the right-hand side is we take on a lot more responsibility. We have to clean up our mess if we delete the car, right? If I delete this car, I also have to go delete this and delete this and delete this. But if I delete this car, all of its parts automatically go away, okay? So you might think, I'd much rather do this one over here. And that's what we're going to do first. We're going to explore that one on the left first, right? But understanding these two extremes is the key to a lot of the parts in this class. So let's build from the bottom up. There is our engine. So it's got one data member called horsepower, and we'll make that public for now. Okay, so that is 120 whatever horsepower engine. And it is got a default constructor. So don't even worry about writing the constructor. It'll be really easy to make an engine. And make sure you make that public, right? That's the big idea. So now we can say engine E. And here's the key takeaway, right? So this orange box is right here, okay? Try to imagine this being a big box that I can reach into so that when I create an instance of the car, that thing is literally inside of the purple square, okay? So if I say my car default constructor, then I can say my car dot E dot horsepower, okay? So the dot E gives me the engine instance, right? And then if I add the dot after that, of course, I'm inside of the orange box and pulling stuff out of those data members. And so that should give me the default value of 120 for my horsepower, okay? Notice no arrows, of course, my car dot E dot horsepower. So you gotta kind of go, okay, this is my car. So my car dot E is this, but that's this. So dot horsepower. Oh yeah, I'm down at this point, okay? And we will be doing a lot of this. And so one of the skills you need to develop is be able to look at the class and then understand how to access those data members. Okay. Now, question? Yeah. Are these two classes in the same file or in different files? They could be either, but for the moment, let's assume they're in the same file. Yeah, let's assume we haven't really separated these things out into .h or .cpp. We've just sort of plowed them up above main. Okay. And these are what are called, we don't have any methods or constructors. They're really called aggregate classes. It's a kind of a special thing we'll talk about. But yeah, for simplicity, we could just put them in one file, all right above main. Now, here's the interesting thing. If I just create a temporary variable called temp E for an engine, and because we have a default constructor, yeah, that engine will start out as 120 horsepower. But let's just think of it as a box called temp E, right? So now I can copy the engine out of the car and overwrite this engine with that engine, okay? So if this, for some reason, happened to be 240 horsepower, it would copy that over the top of that by a simple equal sign. So temp E equals my car dot E, okay? Obviously, we can't say temp E equals my car because temp E is an engine and my car is a car, right? But my car dot E is, of course, the engine. So all things apples to apples line up. And so now we've got a copy, not a pointer, but a copy of the data has kind of moved into this box over here. Okay? It's like we poured this box out into this box. Okay. So that's a key thing. They are not linked in any way. We just sort of stole the data out of the engine, copied it over to temp E. Okay. So we can say my car dot E dot horsepower equals 240. And now the really important understanding here is we've changed the engine inside of the car, but we have not changed temp E. Okay. So this is a key understanding when we use class composition like this. The temp E is a copy, not a pointer to the engine. Okay. And we'll see the other side of that here in a little bit. Okay. And it's kind of weird to think of just copying entire engines over, but that's totally okay to do as long as we design our class correctly, okay? Let's sort of add the wheels here. So if we want to add the wheels, this is where things get interesting. So the engine was easy. There's only one of those. So assuming we have a class that's outside, just floating in my main.cpp file, but it's not like the code isn't inside the car. We want to actually create data members of the class. So we can create an array of 4 instances of wheels, assuming we have a default constructor over here. So when we create a car, it's gonna be like, okay, I know how to make one of those, and I know how to make 4 of those. And now we have 4 instances, all like 4 boxes sort of sitting next to each other, box, 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 because that's what an array is. But each one of them is a wheel, right? So that's okay too, right? And now we'll sort of kind of fill out some of our other parts here, right? So this is what we want to try to do. So we'll do this one together here in just a second to kind of bring all this into focus. Okay. So the really important thing about using the array in this way is we must have a default constructor. Took me a while to figure that one out when I first started trying to create arrays of instances. We have to have a default constructor for that to work. Okay. So let's take a look at this. So you could, by the way, and feel free to do this if you want to deviate here. We'll go over both solutions, but compare the difference between an array of 4 instances and a vector of wheels, which is initially empty. So think of this as an accordion with nothing in it, and this as an array with 4 things created right away. So when I create this car, I get 4 wheels. When I create this car, I get no wheels unless my constructor adds the wheels for me. Okay. So by default, there's no wheels in that thing. Okay. So you get to choose, but it has a little bit of an impact on the work you need to do inside of your constructor. But otherwise, as many of you might remember, our print wheels method is going to probably be identical no matter which path we choose here, right? But the constructor might need to do some special stuff. Okay. So kind of hard to say which is best. Really kind of depends on whether you're going to be adding extra wheels to your car after you create an instance of it, or whether you're just going to have a 4-wheel car all the time. Okay. There's probably a lot of reasons to go with this path over here, but there's nothing wrong with that. I tend to use arrays a lot. Okay. Okay, so let's try this. And note, in this particular case, to simplify for class, we're not going to separate these into .h and .cpp. So let's learn the composition idea first. So follow the good old-fashioned all-in-one kind of class implementation strategy here. So create a new class called engine. I'll show you the solution for this so you can do it. New class called wheel. Just give it a public integer member, horsepower and miles, or if you want to call it radius for your wheels. It was kind of a silly choice to put miles on my wheels, but that's what I did. And then inside of your car, W will be a private data member type, and it can be array or vector of those, right? So you can create an array of wheels with 4 wheels or 100 wheels or 1,000 wheels if you like. And then we will do our car constructor. Oh, I guess we are gonna do it out of class. We're just not gonna separate it into the .h and CPP. So sorry, let me bring you to the code solution so you can kind of see that. Let me just jump to the solution for the engine class. So for folks who are, doing this, really simple, just throw up a class there, make it public, give it some horsepower, right? And you might say, is this a prototype or is this like the actual thing? This has a special name called an aggregate class because it's kind of both, right? It's both the prototype and the actual thing. It's just so simple. It's got a special name. Okay. Don't have to worry about separating that thing into 2 different things. But what's nice is I could say engine E equals curly braces 500, and C++ goes, oh, I'll just pour water over that and turn it into an engine, right? That's what aggregate classes allow us to do. I can just shove these curly braces kind of thing out there, and it goes, oh, okay, that goes in there. Okay, now I know how to turn that 500 into an engine, okay? So that's just a little bit of a side note, not the main show here, right? So here is our wheel class, same kind of thing. It's an aggregate class. Make sure you make it public. That's really important, okay? And we could do that if we wanted to, just to exercise. And then here's our car class. There's the engine. There's our wheels, kind of like we were seeing, right? And then we have our prototype. If you want to do it out of class, just remember our formula for doing that, right? We're going to, down below here in the same file, we can do our out of class implementations, okay? So up here, the defaults are inside of our prototype, okay? All inside of main.cpp for today, right? But this is essentially what we would do in a .h file if we were separating it out, okay? We'll just stack it on top, okay? And then here's our out of class constructor. Class resolution operator constructor. Okay, no defaults, right? We left those up above on the previous page. And look what we're doing. We're kind of initializing all of our wheels to some initial mileage. Okay, it's kind of silly. I should have said radius, right? Radius, radius, radius. That would have made more sense in the real world. Okay, but we're reaching into array position 0, which is the 0th instance of our wheel that was constructed automatically. And we're just using the same kind of initialization value for all of that. Okay. So this is pretty typical of what a constructor might do. Okay. It's just dressing up data members inside of this subclass. Okay. All contained inside of the car. Okay. So from a memory footprint, you can literally think of your car instance as including all parts of the car in this strategy. Everything is in the box with the car. And I wouldn't say fully contiguous in memory, but pretty darn close. And that's probably something we could figure out if we wanted to dig a little deeper. But let's look at what it would look like if we went with we'll just do our other methods first. So if I want to print the engine horsepower from the car. So this is a car method, and we're going to reach into the engine and grab its public horsepower value. So this is really important because the car owns this method, but it's got to reach into some other class to figure out what it has. And that's why, for the moment, it's so important for that member to be public inside of the engine class. So we can reach inside and grab that as part of our car method, okay? And then same for the wheels. So we could use a for loop, or we could just do it manually like that, okay? Here's all the miles on my wheels, or the radius, or whatever, right? Again, class, type out there, okay? So those are my methods. Now, the vector constructor is kind of fun, right? So let's say we want to go with a vector, right? And there's our prototype. A little different. It's really only different right here. Everything else is the same so far, right? Defaults are there. The constructor for the vector is this. Push back, push back, push back. So we're going to use this form a lot. And you're going to look at that and go, what am I pushing into the wheel? Well, wheel is a vector, so we have to push back the right kind of thing. And this has to be a wheel, okay? Because if we go back to our data member, it's a wheel vector. So how can we push a mile in there, which is an integer? Well, when we surround it with the curly braces, C++ realizes, oh, you want me to turn that into a wheel because you're a wheel vector. So it kind of pours water on it, reconstitutes it into a wheel with that many miles, and we're off and running, okay? So our constructor is just kind of filling that thing up with wheels, or we could do something a little more clever like this. So this is a special method offered by the vector class that allows us to do that 4 times in one go, okay? So for those of us who like digging into like a little more special methods, you can do it that way, and that's kind of a cool way to do it, okay? But this is a little bit maybe more what we're familiar with, okay? And you can even do that in a loop. So if somebody said, I want 500 wheels on my car, they could give me 500, right? And in this case with the vector, I could have a for loop and just add 500 wheels, okay? Or if this was cars in a game that were racing, I could maybe in a higher level create 500 cars that way in the racing game class, okay? Probably we're going to see this approach in some of our risk classes when we implement them, okay? So that is what we call composition. We compose the car out of classes, instances that are contained inside. It's like a box of all kinds of stuff. That is different than saying we want to do it with pointers. So remember our different approaches. So we're going to kind of go look at this one over here, okay? So the only thing that's going to be contained inside of our car is going to be a pointer, 64-bit pointer, or a vector of 64-bit pointers, Okay. And we'll come back to that when we get to that part of the code. But if we just want to kind of have one wheel, then that's going to be one pointer. If we wanted four wheels, we're going to have four pointers, right? So we'll look at that here in just a second. Okay. So here's my car class, right, in code. Okay. The engine doesn't really change. So if I wanted to give my car an engine in main, I could do it if this is public. So I could say, okay, there's my car instance. It has no engine until I give it an engine, right? So here's how I can create a new engine, right? So if I had access to a pointer, somehow I could say that variable equals a new engine, and the pointer goes into that variable, okay? So that's what we really want to do, okay? So our constructor is going to need to actually put something there for us. And once it does, we can say my car dot e-pointer arrow. Arrow gets us to the engine, and then we can reach inside of the engine and get the horsepower, okay? So the e-pointer is a dot access to the car, but now we're following a pointer from that e-pointer to the instance of the engine. Okay, we'll show you the code for all this here in a second. But one interesting thing you want to keep in mind is what happens if we try to grab a hold of that engine now? So if I say I have a temporary pointer variable and I want to set it equal to my car.ePointer, we've basically now pointed at the engine for someone else's car. So this is your car, and I just stole your pointer to your engine from inside of your car, and now I can muck around with your engine from over here, okay? So that is not the same as the previous situation where we literally made a copy of the whole engine and they were separate. Now these two things are linked. So if I were to use temp E to change the engine, it's going to change your engine out from under you. Like it's going to change the horsepower or whatever. Okay. Which could be good or it could be bad, right? Maybe that's what we want to do is have a reference to that or a pointer to that. But two different strategies for building our data structure. Okay. So just a couple basic things. If we have a null pointer, that's just the zero address. That means it's a special address in your computer's memory where we say, yeah, okay, zero means there's nothing there, okay? New always returns a pointer. Always, 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 always. Pointer of what? Pointer to a new instance of the engine with default constructor. Notice there's no parentheses over here telling us what kind of engine to make. It's just give me a default engine, okay? So then that's a pointer, so that's followed by an arrow, okay? E-pointer horsepower. So considering our vector, we could do this. W.pushback new wheel. So that pushes back a pointer into the vector. So the vector is not holding on to an instance, right? My vector is a wheel star vector, okay? It's holding, you can almost just throw away the wheel and say, it's a vector of addresses. What kind of addresses? Wheel addresses, okay? So we're putting that in there, and then maybe we add another one and another one, okay? And now we can go to the second wheel and follow the pointer to the miles for that wheel. Not a dot, but an arrow there because we put pointers in the vector, pointer in the vector, okay? So these two extremes are just great contrasting kind of approaches, and they help us work on our understanding of syntax. So let's see if we can add wheels and engine pointers, like engine pointers for both of these to our car class, okay? So these are our data members. Remember, there's no pointers in here initially, so our constructor has a little more work to do. We're going to dynamically allocate an engine and wheels for each of these things, okay? And we use pushback and new engine or new wheels to actually do that, okay? And then we can kind of go initialize the horsepower and the mileage and everything using our arrow pointers, okay? So let's take a look at that together. And remember, what does W have? It has pointers. So 0 gives us a pointer, and then we follow that pointer into the wheel, okay? I'm gonna help you guys shore that up. So here's our car, empty vector, kind of a dangerous pointer here. We probably should have said equals null pointer. That would have been better practice, right? Sorry for my writing. And then our constructor can do with it what we want. Here's the prototype, right? So we're just sort of setting ourselves up. This would be our .h file if we were breaking it out into a separate file, right? That's our prototype. So our out of class constructor, give me a new engine, set its horsepower to what somebody wants for their car, and then create a bunch of wheels, right? And, or we could do the fancy thing, say w.assign 4-wheel, okay? And then I could come back and change their mileage. Now, some of you may be wondering, why not just use the constructor arguments for our wheel? Why do we have to do this in 2 steps? So it is true, if we go back to our wheel just briefly, where do we have our wheel? Sorry for the jumping around. So I guess I don't have my wheel. But notice we didn't have any constructors here. If I gave my wheel a constructor, I could have fed the mileage directly in via the new statement. Sorry for that. So I could have said wheel parenthesis underscore HP for each one of these things, and it would have been ready to go right away. We could sort of drive off the lot. But since we don't have that constructor, we got to come back and manually assign those things, okay? But we could have added an extra pair of parentheses in there to do that, okay? Okay, a lot of syntax, I know. All right, so now just printing out the engine, we just got to remember, okay, it's an out of class implementation. What's my data member? Oh yeah, e-pointer, arrow, horsepower, right? Engine, jumping into the engine, get the horsepower, okay? Print wheels, same kind of thing. W0, W1, W2, W3, or a for loop, etc. Okay. Oops. So that is the difference between kind of wrapping it on inside and hanging it on the outside. And we'll see lots of examples of that and the pros and cons of that. But that's a good one to come back to. I think you'll see some quiz questions in 2 weeks on that. So maybe just, think about this practice problem when you get to that point. Okay. Any final questions before we jump into friends? Okay. Okay, so before I leave this slide, I'll remind you that in our engine and our wheels, we made our data members public. And the reason we made them public was because the car wants to be able to reach in the box and print out something. My colors are all messed up here, right? So it wants to be able to reach in the wheel, even though it's the car that's doing the reaching, okay? The only reason we're allowed to do that is because we made those public. So friends are a way that we can allow ourselves to reach into a class that might otherwise be private, okay? So here you see us with our public horsepower, everything's great, okay? But a lot of times we make our data members private because we don't want people mucking around with them. So if we do that, okay, so we take that public and we change it to private, we now have a problem because our print method will no longer work. We'll get a compiler error that says you are not allowed to have access to that or that. And so we get into this back and forth of like, should we be public or should we be private? Okay. So you can do this or not. I'll just show you, but it's sometimes helpful to see the error, right? So let's just pop in there real quick. Program IZ, little refresh here. Do it again. I know it's there. I know it's there. It's like the first time it's getting pulled up. Try 4. There it is. Okay. So here's my public. It all runs just fine. But if I change this, of course, to private, right, I'll just even change one, the horsepower. You see the error. And it's just ugly. It says, hey, horsepower is private. On line 60, you can't have access to that. So what's line 60? Oh yeah, it's me trying to just get my car up and going. Okay. So that is kind of the problem. Okay, if you do it. Okay, so we want a fix for that so we can still keep things private, but have access between friends. Okay, so I have my ant and bat example. It's kind of silly. The bat has no friends, right? The ant has decided that the bat is its friend. Okay, so this allows the bat to have an ant kind of inside of it, which it can have anyway. But the thing that it really wants to do is reach inside the ant and modify its value. Okay. So the ant over here has a val from A, right? I don't know why I called it that, but so that's what happens if we say friend bat inside of the ant class. Okay. So that is the very simple syntax that allows one-way access from the bat to the ant's data members. Okay. And if we want it to go in both directions, then bat needs to declare ant its friend. Okay. So a really simple syntax. Okay. Open it up in one or both directions, and now we can kind of change or print out at will, even though it might be private, right? Private over here. Okay. So friendship is one directional, maybe kind of like Facebook, right? So if you want to do this, try it out just so you get familiar with the syntax again. It is friend class bat, right? So let's take a look at our code here for the engine. Okay. So we want the car to be able to reach into the engine and reach into the wheel. So we would say friend class car, right? Like that. I'll just tab it over. Okay. Friend class wheel. Friend class wheel. Oops, sorry. Car. Car. Okay. Should just be that simple. And now we're back in business. Okay. That's all friends are about, right? Opening a pathway, usually when we're composing classes like we were actually doing there. Okay. Like so. Just as easy as that. Okay. It turns out you can get even more narrow focus too. You can be like, oh, the constructor is just my friend, or oh, this method is just my friend, to really narrow that down. But we've kind of did it on a class-wide basis here. Okay. Okay, so I think I probably summarized all this stuff, but if you're coming back to read and quick study this stuff down the road, you might want to come to this slide. But we'll come back to friends in the next couple weeks or so. We just kind of want to introduce it so we can kind of write some better code in the meantime. Okay. And when we talk about inheritance, which we eventually will, not in the way of the ancestor class, but that we saw, but a new kind of inheritance we'll talk about. Friendship we'll find is not inherited. So we'll see some of the caveats around that when we get to that point. Okay. Okay. We got about 15 minutes left. I just want to show you this because there's a few, maybe some, good anchoring ideas here. So feel free to not follow along because I'm going to kind of try to get through this so we can get you to the lab a little early. But this is just another example of a class that we find are necessary sometimes. Like let's say that we want to design a game where we want to record a position to know whether two positions on the board are the same, right? So the idea of a position class is it's got two members, like a row and a column, let's say, okay? So we'd like to actually bind them together and create instances of a position, okay? And that could be for a lot of things. It could be for math and geometry and all sorts of stuff. But we'll think about it in the game context of idea of a game. And maybe our position might also eventually tell us whether there's an X or an O there, right? So we have a position, or something at a position. So right now we're just going to think about it as a position. So let's kind of think about how we're going to do that. We want to be able to create an instance of one with some default constructor that say puts that position at 0, 0. Like that's just a convenience. Or I might want a setter that says now change that to 3, 4. Okay, so we're updating the position of P0, updating it again, creating a P1 at 1, 2. Okay, so that's a totally new variable, P2, etc. Right? And we also want to do this. I want to know whether these two things are equal. Okay. So this really gets to our overloaded operator, operator equals equals. So our position class really should have understanding of what it means to determine whether two positions are equal. Okay. And you can probably guess what that's going to look like. And a couple other convenience functions. Okay. So here's our class, private, row call, public. We'll come back to our constructor. We got a setter, right? Get string. This is the prototype and the overload. Operator equals equals. And then what is the thing that we're comparing against? It's going to be an argument that is a position type, right? What am I equivalent to with some other position? So we'll look at that here in a second. So the separation of these things is going to roughly look like this, right? Got our dot H on the left, our dot CPP, and it's going to include the dot H. So we're going to have a little include up here to pull that in when it's compile time, okay? So we'll take a look at the code for that, okay? So there's our prototype. Defaults go in the dot H, not in the CPP, okay? So they're identical except for that, and we got to add our kind of our class designation to the constructor, okay? Okay. So no namespaces in our .h files. That's the golden rule. And we'll look at some narrow, okay things. But for now, we're going to leave that out of our .h files because we would get screamed at by everyone we interview with if we show them code with that in there, right? So everywhere we use string, std string, everywhere endl. So those of you who hate endl, this is a good reason to switch over to \n if you like. Right? You can just kind of go with \n. Otherwise, you got to do std ndl or std vector. There's a lot of them, unfortunately. Okay, and you'll discover them, by compiler, essentially. Death by compiler. So it is tedious, but we're going to start practicing that. So let's see if we can actually do this. You don't have to do this. I'll show you how to do it. But you can kind of click into Program IZ Pro, kind of see what it looks like, or you can click into the Replit one. Let me see if I can get us into Pro here. I did log in before. So for those of you who haven't seen it yet, it's pretty similar to Replit, right? So we have our main.cpp over here. Okay, there are some things that we don't have yet. We can't quite yet pull the center bar around, so I know your code wraps around. But here's our main.cpp. Here's our, let's go to position.h actually, position.h, right? So we have our constructor prototype, our setter prototype, our get string prototype, etc., and end of class, okay? And if we were going to have defaults, they're here too, right? In the .h. Over to the CPP, right? So we got to say pound include, right? So we got to start out. I won't go through all this. I'll cut to the slides here real quick. But pound include quote, position capital P, position .h. That's a convention, right? And anything that we do is going to be data type, right? Followed by position, double colon, and then name of method, right? Name of method, whatever that is, right? I'm just kind of giving you some pseudocode here. Okay, so let me cut you to back over to the solutions. You can kind of fill this stuff in if you like. Okay, so here's our position constructor, right? Int C, no defaults there. If the row is greater than 0, okay, set it. Otherwise, set it back to 0. Or we throw an exception, right? Some of you might vaguely remember exceptions. That's an alternative way to throw up your hands in a constructor and say, I don't have what I need here, right? But we're going to cheat and just force the row to location to 0, okay? Same for the column. So that's our constructor, okay? And our set method, as you can imagine, right? We don't want to let it set something in the negative range. And you can do all sorts of extra stuff there. And when you are working in advanced code in this class, I know it is tedious to add messages to your methods, but it will save you so much time. You can always put a comment and turn it off. Or what I like to do is say, if debug, do this, right? And then I have a global variable or add a debug variable to my method that allows me to turn things on and off. But it can save you a lot of time, okay? So keep that in mind, especially if you're running into bugs. And then make sure we're always returning. So here you might remember this from comp 130. It's like, did I set it? Yes, I did set it. Did I set it? No, I did not set it. Okay. Sometimes our setters can benefit from having that little extra piece of information, but that's just a nice to have. Okay. Okay, get string. Okay, I won't spend a lot of time on these, but you can kind of flesh that out a little bit. Again, class type, including our std over there. And we are returning a string, so we're just concatenating, 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 concatenating. Okay. That's our type. And then our operator overload. So if they're both equivalent, if my row is equal to your row, and my column is equal to your column, then return true. Otherwise, return false. So that's our overloaded operator equals. So now we can compare positions. And we could even do greater than or equal to if we wanted to, right? Okay. So just another example, okay? So that brings us to our lab, which I like a lot, actually, even though I do not understand chemistry, really, and I'm often reminded that I get it wrong. Let's think about how we can do atoms and molecules using compositional classes, just like our car and engine. So I have an atom, I want to have an integer number of protons and an integer number of neutrons. And if I remember correctly, we can calculate the number of electrons from that in most cases, but I'm going to just go with that. And then over here, I want to have a vector of atoms. And I love this because it's like, oh, okay, I can actually kind of build up some molecules here. Okay. And then I could have a method that prints out some particular atom. So if I have 5 atoms, then printing the 5th one, right? If there were 6, sorry, printing the 5th one would be a number 4. Sorry, start that over again. There are 5 atoms, 4 would be the last atom. So our print vector index is really just like, hey, go get me that one, okay? So these are the things that we want to build, okay? And when you print this out, you could say the number 0 atom of water has 1 proton, right? If this is a water molecule, for example, okay? So let me get you the rest of the information. And we're going to make a molecule a friend of the atom so that we can keep these things private over here, okay? So, and this is the fun part. If you like, or know about molecules, have at it. Go look up some fun molecules, right? Make yourself a hydrogen, make yourself an oxygen, create a water molecule, and then start pushing back copies of atoms. Okay. So notice what we're doing. We're going into the public atoms vector, pushing back a copy of hydrogen, pushing back another copy of hydrogen, pushing back an oxygen. Okay, so here's our H2O. Okay. Pushback always makes a copy of whatever you're giving it. Okay. So whatever you put in there, pushback is like a little cloning machine. It just makes a copy. And so now I could say molecule has water.atoms.size atoms. So I'm reaching in the box, grabbing the vector, asking for its size method, right? This is just the size method for my vector, okay? Or I can call the method that is part of the water molecule and say water dot print atom 0. So that should get me hydrogen, okay? Okay. And if I knew something about chemistry, I could figure out how to add two molecules together and come up with something new, right? I would have to overload the add operator, and now I could be like, ooh, I'm actually doing computational chemistry, right, in C++. That would be kind of fun to do, okay? And I'm sure somebody out there has actually done that. So again, we're just going to try to implement that. So just a quick peek at a Program IZ Pro here. Actually, I'll start with Program IZ. So if you don't have or just really don't want to use Pro or Replit, then just use our stacking strategy. Put your .h up here, okay? And then put your out of class atom methods here. And you'll see I've got your .h for the molecule over here. So you'll just put your print atom method over here. So there's very, very few methods you got to actually do here, right? So it's just about getting used to that. But if you want to do it the more kind of, oops, undo. You want to do it the more, realistic way, hop on over or go to Visual Studio Code, fine as well. And you'll see we have these properly set up. So our .h is over here for molecule. And notice, this is crucial, we got to pull in both the atom.h, we got to pull in the atom.h into the molecule.h. That's going to be a surprise for folks, right? So if you're doing this, don't forget the atom.h. And then the molecule, let's see, where do we go? Over atom.h is here, molecules.h, and then atom.cpp you'll have to implement. Okay, so this is maybe going to get you a little more ready for tic-tac-toe and all of our other programs if you have the opportunity to do it that way. Okay, and that is it. Any questions? All right, very good. Stay dry, everybody. We'll see you on Tuesday. Send me emails if you have questions. Okay, thank you.